Welcome to lecture series on advanced geotechnical engineering, and we are in module 3 and lecture 8 on compressibility and consolidation of soils. Module 3 lecture 8 on compressibility and consolidation. So, in this lecture we are going to discuss about the compression curves, particularly under different conditions like when it is sample is subjected to compression and unloading, that is recompression, and we also discuss about what will happen when the load increment ratios are kept longer or when you have low load increment ratios, and what will happen if a particular load is kept for long duration, that is the effect of the secondary consolidation. And thereafter we will introduce ourselves to the need for the radial consolidation, and then in the next lecture we will be discussing about the methods for accelerating consolidation settlements. So, let us before going into the details of whatever we have just discussed, now let us see. Now, let us look into the effect of sample disturbance on E log sigma dash curves, especially for normally consolidated and over consolidated clays. So, first consider normally consolidated clay, and in this particular figure where void ratio versus sigma dash on the logarithmic scale is shown here, and here if a normally consolidated soil, that is the soil which is actually having higher water content and where this pre-consolidation pressure, the present effective pressure is only sigma naught dash, and if that is the maximum pressure whatever the soil has seen, then in that case in the field what we actually see is the straight line is the virgin compression curve. So, this is also called as field normally consolidated line or field compression curve. But when we take a sample and if it is subjected to, generally the sampling is done by using an appropriate sampler, and which actually gives the least disturbance. But if you have a laboratory specimen which is tested, which is actually obtained with careful recovery, then what we get, this E log sigma dash curve is like this. This is indicated as a curve 2 in the figure. But if the same specimen is actually remolded and reconsolidated, then actually what we will have is the remolded specimen will have this type of E log sigma dash curve. So, if you look into this, all 1, 2, 3 the field compression line and laboratory undistributed sample, which is indicated as curve 2, that is the obtained from the consolidation test on a carefully recovered specimen, and curve 3 which is obtained from consolidation test on a remolded specimen. So, if you look into this at a certain stress when it actually has been subjected, then all they will actually meet at a point which is the 0.4 E naught, where E naught is the initial void ratio at sigma naught dash, that is the current overburden pressure. So, if you look into this the difference, the distinct difference between field compression curve and these laboratory undistributed sample is because of the the degree of disturbance what actually enters into the testing. And the curve 3, which is if the same soil which is actually tested in 2 is say remolded and reconsolidated, then what we get is this so called E log sigma dash curve, which is in this form, and where actually it appears. And one more thing is that if you look into this for remolded specimen, very difficult to distinguish where is the pre-consolidation pressure. So, if you look into the, as you go away from the with the degree of disturbance, very difficult to distinguish its correct the stress history what the sample actually has been subjected. So, in case of a normally consolidated clay, what we have is that the field compression curve and the E log sigma dash curve for the laboratory test specimen tested with carefully on a carefully recovered specimen, and the curve 3 which is obtained from the remolded specimen, they actually meet at a point which is actually approximated as 0.4 E naught or 0.42 E naught according to Terzaghi and Peck 1967. Now let us see what will happen for a over consolidated clay. So as you all know that the soil actually has seen a pressure which is actually much more than the current present overburden pressure. So you can see that, so because of this the initial portion of this curve is actually flatter, and then once this stress which is actually transferred to the soil is actually more than what it has actually seen, then it will change into the so called normally consolidated mode again. So you can see that the two limbs which are actually there, this is actually the portion AB and portion BC. So this dotted line is the field compression, this dotted line BC is the virgin compression curve for the so called can be obtained for the OC clay in the field, and AB portion and BC portion, these two are the two segments which will be there, and the slope of this line AB is recompression index, and slope of this line BC is the the compression index CC. Now if you are actually testing an undisturbed sample, you can see that the degree of the initial portion is flatter, and then again it changes into the normally consolidated mode, and again it meets at a point C, and when the rebound actually happens for a that means that once the unloading actually happens here in the laboratory, CF segment is the laboratory unloading portion. So you can see here that according to Schmettmann 1953, he concluded that the slope of this line and the slope of this line AB are almost identical. So Schmettmann 1953, he concluded that the field compression branch AB approximately has the same slope as the laboratory unloading branch CF. So in case of the over consolidated clay, and what we have is that the two segments AB and BC. So that is the reason why while discussing the settlements, and we have to see get the pre-consolidation pressure. After getting the pre-consolidation pressure, then we have to, if you are actually having a if this is the field compression curve which you are adopting for the design, suppose if this is the stress which is actually has been subjected, then you have to calculate for the settlement for this portion, and you have to calculate for the settlement for this portion. So that is what actually we have discussed in the previous lecture. So in this the curve 1 is the E log sigma dash variation for undisturbed over consolidated clay in the field. So this is actually idealized for the field conditions, but if we are actually having the sample recovered from the same site, same portion where actually with a little degree of disturbance, then we can see that this is how what we get is that laboratory undisturbed sample will yield E log sigma curve like this, and then CF is the unloading branch, and the slope of this AB and CF are found to be identical. And one more thing is that CR is approximately 1/5 to the 1/10 of CC. So in the case of absence of data, and it can be assumed that the CR, the recompression index, is 1/5 to 1/10 of CC. The CC is nothing but the compression index, the slope of the normally consolidated portion. Now let us see what will happen if we are actually having deviations from the consolidation test, and if the standard consolidation tests are conducted with a soil specimen having a thickness of say 25 mm or 25.4 mm, in which the load on the specimen is doubled every 24 hours. This is the standard. The standard consolidation tests or iodometer tests are conducted with a soil specimen having a thickness of 25.4 mm, in which the load on the specimen is doubled every 24 hours in the laboratory. So this means that the delta sigma by sigma dash is equal to 1. The delta sigma by sigma. Delta sigma is nothing but the change in load towards the initial load. So delta sigma by sigma dash is equal to 1. Load increment ratio is always maintained as 1. So the question is that what will happen if load increment ratio is greater than 1? What will happen if load increment ratio is less than 1? So what will be the effect of any deviation from the standard procedure? Like if you do not keep for 24 hours, if you keep for long hours, what will happen? If you keep for less than 24 hours, what will happen? So the striking changes in the shape of the compression time curves for one dimensional consolidation tests are noticed if the magnitude of delta sigma by sigma dash is less than 0.25. So, it has been noticed that the several investigators actually have carried out, and the striking changes in the shape of the compression time curves were obtained for the one dimensional consolidation test if the magnitude of delta sigma by sigma dash is less than 0.25. So, according to Leenortz and Alta-Scheffel 1964, they conducted several tests on Mexico City clay with the different load increment ratios and with variation of excess pore water pressure measurement with the time. So, conducted the several consolidation tests on Mexico City clay with the different load increment ratios and variation of excess pore water pressure measurement. So, in this particular slide, time, which is actually shown on the x axis, the specimen height is actually shown here. You can see that this is delta sigma by sigma dash greater than or equal to 1, and here delta sigma by sigma dash less than 0.25. That means that as the delta sigma by sigma, so this is equal to or the greater than 1 or found to be somewhat in this line, and when delta sigma by sigma dash is less than 1, it actually migrates in this direction. So, for delta sigma by sigma dash less than 0.25, the position of the end of the primary consolidation is somewhat difficult to resolve, and also the C alpha by Cc, that C alpha is nothing but the secondary compression index to the primary consolidation, the compression index in the primary consolidation range increases with the decrease of the load increment ratio. So, what we can see is that for delta sigma by sigma dash less than 0.25, the position of the end of the primary consolidation is somewhat difficult to resolve. We will not be able to, whether you cannot say whether it is here or here, or, and also it has been noted down that you can see that the distinct difference of excess pore water pressure dissipations which actually happens. Excess pore water pressure here is that delta sigma by sigma dash is actually happening less than 0.25, it is actually much before, and then whereas in case of delta sigma by sigma dash greater than or equal to 1, it is actually happening at much later. That can be understood, but here the reduction in the early dissipation can be understood because of the low load, but here what is actually happening is that here the very difficult to distinguish the so called the end of the primary consolidation process, and another thing is that the ratio of C alpha by Cc increases with the decrease of the load increment ratio. So, as we go in this direction, what will happen is that the ratio of C alpha by Cc increases. C alpha by Cc, that is ratio of secondary compression index to compression index increases. Now, when delta sigma by sigma dash is say less than 1, so here void ratio and log sigma dash are plotted here, and this is the case, the standard E log P curve for delta sigma by sigma dash is equal to 1. If it is less than 1, it actually will be right above the the conventional iodometer test result. If it is greater than 1, it is actually somewhere here. So, if you look into this here for a given load and more when you have got delta sigma by sigma dash greater than 1, so the void ratio decrease is high, but when you have got delta sigma by sigma dash is less than 1, the percentage decrease in void ratio is low when you compared with these two. So, when delta sigma by sigma dash less than 1, the ability of individual soil particles to readjust to their position is small. So, when delta sigma by sigma dash is less than 1, the ability of soil particles to readjust to their positions is very small, and which results in a smaller compression compared to delta sigma by sigma dash greater than or equal to 1. So, what we are actually trying to conclude from this slide is that when delta sigma by sigma dash less than 1, the ability of individual soil particles to readjust to their positions is small, which results in a smaller compression compared to delta sigma by sigma dash greater than or equal to 1. So, that is the reason why we actually have a distinct difference when you actually have variation of the delta sigma by sigma dash. Now, what will happen? Let us see that the load duration. Suppose if you conventionally we keep 24 hours, each load increment ratio which is actually with delta sigma by sigma dash is equal to 1, is maintained for 24 hours. So, in a conventional consolidation test in which a small specimen left under a given load for about a day, a certain amount of secondary consolidation takes place before the next load increment is added. So, that is possible, but so in this particular slide what we have actually seen is that void ratio and the sigma dash, that is the log scale, that is the the log sigma dash curve, this log sigma dash axis. Now, what we are actually having is that, and the curve A is the end of the primary consolidation, load duration just sufficient for the primary consolidation. So, load duration is just sufficient for the primary consolidation when you plot, and this what is actually referred here in as curve A, and curve B is the load duration with 24-hour load increment duration. That means that this test actually is strictly conducted with 24-hour load duration. When you have more than 24 hours load duration, you can see that the curve actually shifts towards, when increasing load duration, E log sigma dash curve actually shifts towards left side. So, what we have is that the sigma C dash, the pre-consolidation pressure is also changing. Previously here it should be this much. So, there is a shift in the pre-consolidation pressure magnitude, and when we actually have just actually sufficient for the end of pre-consolidation, you actually have different pre-consolidation. So, it can be noted that different values of magnitudes of pre-consolidation pressure. So, for soils that display secondary compression, volume changes occur after the end of primary consolidation, because not all soils actually express secondary consolidation. For soils that display secondary compression, volume changes occur after the end of primary consolidation if each load increment is in place for a longer period. So, most common for the are the normally consolidated and likely over consolidated soils up to OCR is equal to 2, and they are referred as the likely over consolidated soils. So, if each load increment is in place for a longer period, what will happen is that normally consolidated or likely over consolidated soils, they actually subjected to a certain degree of secondary compression, and heavily over consolidated soils are less prone for the secondary compression. So, because heavily over consolidated soils are less prone for the secondary compression, and the shape of the curves becomes less distinct with a longer period of duration, and it is more difficult to sigma naught. So, with the shapes of the curves they keep on changing, and with the longer duration it is difficult to predict, it is difficult to determine sigma naught C, that is the pre-consolidation pressure determination is difficult here. So, if you see this hatched portion here, and this volume change actually occurs due to the secondary compression, this volume change, because that same load increment, that load duration kept for a longer duration. So, what will happen is that the secondary compression component is actually entering into the phenomena, into the picture, and it actually results in the volume change, and it causes this is attributed to the secondary compression. So, what we understood is that if you are actually keeping the load duration slightly for longer hours, then what we actually have seeing is that there is certain amount of for over consolidated soils which is has the negligible influence, because they are actually not having much of the secondary consolidation component will be very low. But when you have the normally consolidated soils and over consolidated soils, likely over consolidated soils, we have we can see the volume changes due to secondary compression significantly. And also one more thing we have discussed is that the shape of the curves become less distinct with a longer period and duration, and it is more difficult to determine pre-consolidation pressure sigma dash C. Now, what will happen? Let us say that sample thickness. Normally, the sample thickness to diameter ratio, we actually have said that diameter to thickness ratio is actually maintained as 3, basically to reduce the sidewall frictions. That is one of the reasons for that. And the second reason is that to have the the epsilon r is equal to 0, and also to represent the one dimensional consolidation only. So, for similar load increment ratios, proportion of the secondary to primary compression increases with a decrease in the sample thickness. So, for if you are having for similar load increment ratios, the proportion of secondary to primary compression increases with a decrease in sample thickness, and also the ratio of secondary to primary compression increases with a decrease in the load settlement ratio. Now, let us see the secondary consolidation or creep effect. So, in this particular slide, where what we see is the E log sigma dash curve again, but we have indicated here three curves. One is curve A and curve B, and there is one curve which is actually for example, after 10,000 years of consolidation. So, in the curve A, what we see is that the sedimentation is actually happening, and this is the current overburden pressure, and then further it is undergoing normally consolidation. And the curve B is after 10,000 years, if the sample is actually subjected to 10,000 years of consolidation, when it is actually subjected, then when it is consolidated, and then what we get is this variation. So, the continued secondary consolidation of a natural clay deposit has some influence on the pre-consolidation pressure. So, the continued secondary consolidation of a natural clay has some influence on the pre-consolidation pressure sigma dash C. A clay that has recently been deposited and come to equilibrium by its own weight can be called as young and normally consolidated clay. A clay that has recently been deposited and comes to equilibrium by its own weight can be called as young and normally consolidated clay. And curve A is for young normally consolidated clay, and wherein sigma C dash is equal to sigma naught dash, and at E naught, that is the at this particular point, that is the initial void ratio, and this is the curve here. If the same clay is allowed to remain undisturbed for about 10,000 years, and for example, under the same effective overburden pressure sigma naught dash, there will be creep of secondary consolidation. This will reduce the void ratio from E naught to E1. Because of the creep effect, the void ratio reduces from E naught to E1. Here you can see that the constant effective stress, the sigma naught dash, which is actually no change actually happened, assume that for the 10,000 years, then the void ratio changes to E1. Now, so the clay may now be called as, so this clay is actually called as aged normally consolidated clay. So, previously if there is fresh deposition of clay is happening, and the reasonably deposited and comes in equilibrium by its own weight, then it is called young normally consolidated clay. And if this subjected to certain amount of secondary creep, and then will reduce the void ratio from E naught to E1 as shown in this slide, and this clay may be now called as the aged normally consolidated clay. Now, if the clay at E1, that is at this particular point, clay at E1, now the initial void ratio for this is that E1, which is actually after 10,000 years, and the effective overburden pressure is sigma naught dash, that is this pressure sigma naught dash, and the curve looks like B, and the pre-consolidation pressure when determined by the standard procedure will be sigma 1 dash. So, when you do the consolidation test on the sample which is actually collected after 10,000 years with the sigma 1 dash is the sigma naught dash as the initial overburden pressure, what you look like is now that pre-consolidation pressure is actually nothing but sigma 1 dash. So, the pre-consolidation pressure when determined by standard procedure, it will be sigma 1 dash. Now, sigma C dash is equal to sigma 1 dash, and which is greater than sigma naught dash. So, this is sometimes referred to as the quasi pre-consolidation effect, more pronounced in the plastic clays. So, this type of behavior is actually more pronounced in the clays of high compressibility and high plasticity, that is CH type of clays, that is the more pronounced in the plastic clays. Jerome in 1972 gave an estimate of the relation between the plasticity index and the ratio of the quasi pre-consolidation pressure to effective overburden pressure, that is sigma dash C by sigma naught dash for the late glacial and post glacial clays. So, for glacial and post glacial clays, so you can see that as the plasticity index value is increasing, there is an increase in ratio of quasi pre-consolidation pressure to the effective overburden pressure sigma naught dash. So, with increase in plasticity index, then this is actually more prominent, and it actually increases sigma c dash by sigma naught dash, which will be high. So, the quasi pre-consolidation effect will be very more pronounced or significant in plastic clays. So, you can see from the table which is given here that increase in the plasticity index value, where the sigma c dash by sigma naught dash, sigma c dash is nothing but quasi pre-consolidation pressure, and sigma naught dash is nothing but effective overburden pressure. So, sigma c dash and sigma naught dash, which is actually they are for late glacial and post glacial clays. Now, after having discussed the effect of load duration and effect of the load increment ratios and effect of secondary consolidation and effect of sample thickness, now let us look into the compression curves and different forms of representation, and particularly for compression and swelling that is in the unloaded zone. So, if a series of load increments is applied to a specimen which is initially wet, and resulting equilibrium states will appear, and as shown below. So, if you look into this here, this specimen, this is the E sigma dash, that is the compression curve, E sigma dash curve, where you can see that the sample actually has been subjected to this curve and up to load E0 to E2, then unload it and then reload it, and then you can see that it joins here, and then it goes it get loaded further, and then after here unloaded again and reloaded here. So, you can see that the cyclic over consolidated sample recompressing and cyclic this is simply over consolidated or the swelling is also called, this limb is actually called as the swelling portion, that is the unloading portion, that is the soil actually bounces back when the load is actually removed. So, this is actually plotted on the E log sigma dash curve. When it is actually plotted, you can see that all this whatever may be the loading, unloading and loading unloading cycles we have, and this line joining this line is actually indicates the compression line, which is actually obtained and close to the field compression line for normally consolidated soils. So, E0, E1, E2, E3, and then unloading and reloading and unloading and reloading. So, whatever the cycles we have, it actually follows that slope. So, this is further indicated, the outermost curve connecting the points when the specimen is in loose possible states is referred as the virgin compression line, that is this line is actually referred as the virgin compression line, E0, E1, E2 is referred as virgin compression line, and because it is strictly the line connecting the equilibrium states, whereas equilibrium states in the sense that for that type of increment load the consolidation is completed and anything, and it is strictly the line connecting the equilibrium states, whereas the consolidation is a term used only for the time dependent process between any pair of. So, it is also this is actually called as virgin compression lines because it is strictly the connecting the equilibrium states, whereas virgin consolidation is something like the consolidation is we have a time dependent process between any pair of equilibrium states. So, the equation for the virgin compression line is given by E is equal to E0 minus Cc by log to the base 10 by sigma dash by sigma naught dash. So, the outermost curve connecting the points when the specimen is in the loose possible states is referred to as the virgin compression line rather than as virgin consolidation line. The reason is due to the fact that the line connecting the equilibrium states, whereas the consolidation is the term used only for the time dependent process between any pair of equilibrium states. Now, this equation of virgin compression line further represented as V in terms of sample volume, in terms of specific volume, that is nothing but nu and is equal to nu naught minus lambda natural logarithm of p by p naught, which is nothing but sigma by sigma naught, and wherein the lambda is a characteristic constant, and the nu naught is the initial specific volume. So, specific volume is nothing but 1 plus E, and then E is these are actually related as the water content, specific gravity and void ratio, they are related with one another. And equation of virgin compression line will be denoted as nu is equal to nu naught minus lambda natural logarithm of P by P naught, and equation for swelling and recompression loop will be represented by a single straight line of the form that is nothing but nu is equal to nu naught minus kappa. This kappa is for the the recompression loop or the swelling loop. So, which is something analogous to swelling index or recompression index, natural logarithm of P by P naught, where lambda and kappa are the characteristic constants for the soil, and virgin compression lambda line represents the irreversible process, whereas the swelling and recompression kappa lines represent the reversal process. So, lambda line represents the, so this is when you plot this line is nothing but the lambda line. So, the lambda line represents the irreversible process, because the soil subjected to irrecoverable changes, and it is actually called as irreversible process, whereas the swelling and recompression kappa lines represent the reversible process. Now, this is further indicated whereas the equation for normal compression line OACD is given by E is equal to E naught minus Cc into log sigma dash z. So, here you can see that E versus sigma dash z for the consolidation compression is actually shown, and this is for the one dimensional compression and the swelling. So, OA, and it is actually at O it is subjected to an effective overburden pressure of sigma naught O, sigma naught, and at point C it actually has been subjected to sigma dash y, that is the it is called as the yield stress, and D is again the load was actually terminated here. So, you can see that at point C the load is stopped and then gone unloaded, that is called unloading, and then that is called also called as the swelling line, and this is called recompression line. So, BA is the recompression path, and then it follows or joins to C and then follows further to D. So, this is again in the normally consolidated mode. So, the same thing is represented in the void ratio versus log sigma dash z. Then what will happen is that this is the slope of the Cc, that this is called as the normal compression line, and at point from the point A and C, they are at this point, and A and C are at this point. In the case of in case of log sigma dash z, you will see at this particular point, and B is at this point where that at the end of swelling or a unloading effect, and then so you can see that sigma naught dash is the overburden pressure here, sigma dash y is the yield stress here, and so you can see here that E kappa is this particular one at this particular point where this recompression or the swelling was complete. So, this equation for the swelling and recompression lines are given as E is equal to E kappa minus Cs into log sigma dash z, and E is equal to E naught into E is equal to E naught minus Cc log sigma dash z is the normal compression line for OACD. The equation for line OACD is given by E is equal to E naught minus Cc log sigma dash z, and for swelling and recompression line it is actually given as ABC, which is nothing but E kappa minus Cs log sigma dash z. Now, since delta V, that change in volume is equal to change in void ratio, and log x to the base 10 is equal to 0.43 times natural logarithm of x, then we get Cc is equal to 2.3 lambda and Cs is equal to 2.3 kappa. So, by using this, we can actually once you substitute this natural logarithm into this logarithmic of base 10, by using this we actually get into this particular relation, they are one and the same. So, for water consolidated soil at a point such as B, the yield stress ratio y naught is given by y naught is equal to sigma naught dash by sigma naught this. So, for a war consolidation soil, that is at a point such as B, the yield stress ratio y naught is given by y naught is equal to sigma naught dash y by sigma naught dash, where sigma naught dash is the current stress and sigma naught dash y is the yield point, which lies at the intersection of the swelling through point B and with the normal compression line. So, with the normal compression line, that is, this is, so we are actually defining here the yield stress. The yield stress is nothing but sigma dash y, ratio of sigma dash y to sigma naught dash. Sigma naught dash y is actually obtained at this particular point, and where it actually has from the normal compression line, where it meets this particular first limb, where the unloading which actually meets the normal compression line, and that is actually is rendered as sigma dash v, and which is sigma dash by v by sigma naught dash, where sigma dash is the current sigma dash O, sigma naught dash O is the current stress, and sigma dash y is the yield point at which it lies at the intersection of the swelling line through B with the normal compression line. Now, let us see the effect of one dimensional consolidation and swelling of soil in the ground due to deposition and erosion. So, we know that deposition and erosion, they are the continuous process, but on the soil layer, which is actually prone for particularly the normally consolidated and now lightly over consolidated soils, they are actually prone for changes because of these actions like deposition and erosion. So, considering this particular slide, an element, soil element, which is actually subjected to vertical stress sigma dash z and horizontal stress sigma dash h, and when the erosion actually, when the deposition happens, what will happen? There is a increase in the soil water burden above this particular point, which is subjected to high stress due to the, so you can see that z dash b is increased here, but when there is erosion takes place, the stress on this actually decreases. For example, you can see this is the, when the erosion takes place from here to here, the unloading is actually happening, that is sigma dash c. So, this is actually indicated by as E is equal to WGS. So, from void ratio and now it is actually indicated with water content here and log sigma dash here. You can see that AB is the recompression line. So, the water content changes from A to B, you can see that the water content decreases and R void ratio decreases. So, A to B, and from B, that is sigma dash B, when it is unloaded, BC is the path which actually takes, and stresses this point is sigma dash C. So, here what is actually happening is that when you have K naught at pressure at rest is defined as sigma horizontal stress by vertical stress, when K naught is equal to 1, when it is actually having elastic equilibrium, then sigma dash z is equal to sigma dash h. So, this is that K naught line which actually indicates. So, this is sigma dash h on the x axis, sigma dash z on the y axis. So, you can see that when the case of deposition is actually happening, you can see that A to B it actually decreases, and B to C you can see that here the K naught values are actually can actually go more than 1, particularly because of this stress effect. So, the one dimensional consolidation in the swelling of soil ground due to deposition erosion is actually depicted, and these actually represent the different water contents because of the type of actions which actually have been subjected. So, for normally consolidated soil and lightly over consolidated soil, sigma dash h is actually less than sigma dash z, and K naught sigma dash h is less than sigma naught h is less than sigma dash z, sigma naught h is less than sigma naught z, and K naught less than 1, that is for normally consolidated soil where the deposition is actually happening. So, this is this path which is actually shown AB here, and while as heavy consolidated over consolidated soils, sigma h greater than sigma z and K naught greater than 1. So, that is because of this, here it actually can have K naught values more than 1 can be obtained. For some heavily over consolidated soils, and because of the stress locking which actually can take place, because of that they exhibit the K naught values very high. Sometimes the K naught value can actually go up to K naught is equal to 3. So here what we are discussing is that for for normally consolidated and lightly over consolidated soils, sigma dash h, the horizontal stress is less than vertical stress and k naught value is less than 1. While for heavily over consolidated soils, sigma dash h is greater than sigma h jet and k naught is actually greater than 1. So an approximation is basically often used to estimate k naught, and which k naught is actually nothing but K1C, where k naught of a normally consolidated clay which is nothing but 1 minus sin phi dash c, and phi dash c is the critical state friction angle, and root over y naught, and the K1C minus root over K0 NC root over y naught. This y naught is nothing but the yield stress ratio, which we have defined earlier. Yield stress ratio is actually nothing but sigma dash y by sigma naught dash, where sigma naught dash is the current stress and sigma dash is the stress at the point yield point, which is the intersection of swelling line through B and with the normal compression line sigma dash B. Now let us see variation of water content in normally consolidated and over consolidated soils. We actually have been pointing out that for normally consolidated soils the water content will be very high, and over consolidated soils the normal content is less, and so consider the variation of water content with the depth for different for a deposit which is lightly eroded, you can see that eroded, that is the depth of erosion which is small, or heavily eroded, that is depth of erosion is very large. So we have two states. This is the stress point A and B, and stresses at point C and D. So this particular soil strata, the elements A and B actually are referring to the way the depth of erosion is relatively small, and in this case the stress element C and D, the depth of erosion is relatively large. That means that the element C and D has been subjected to very high past pressures, A and B subjected to low pressures, low degree of pressures. Now what will happen is that for the lightly eroded soil, the difference between the water content at point A and B is relatively large, while for heavily eroded soil the difference between water content and C and D is much smaller. So here what we have is that water content versus sigma dash z is shown here. So you can see that this is the compression line, loading and unloading. So this first limb actually refers to sigma dash A, and this is unloading. So we have done loading and unloading portion and loading portion, which simplified here, and this is point B, the limb point B, and you can see here there is a distinct change in the water content here. Here there is marked, there is no negligible or marginal change in the water content for the in this particular portion. So for the lightly eroded soil, the difference between the water content A and B is relatively large, while for heavily eroded soil the difference between the water contents at C and D is smaller. So that is what actually has been indicated here. So here if you look into this, this is for the normally consolidated soils or heavily lightly over consolidated soils, and these are the heavily over consolidated soils. So you can see that the C and D, so this is water content versus the depth, and the element A, sigma dash A and sigma dash B. Low water contents at C and D are attributed to the very large past stresses. So the soil actually has been subjected to past stresses. So the low water contents here recorded, and you can see that this is also negligible variation, but here you can see that with the depth of course there is a decrease in water content, but thing is that here there is a large variation, but here there is a negligible or marginal variation. So the reason is that actually basically attributed to that the soil elements at C and D were actually has been subjected to very large past stresses. Now let us, after having discussed these the effects of the load increment ratios and the duration, let us look into some example problems, and in this example an iodometer test was performed on a clay sample of 30 mm thick and drained at both sides. That means that we have kept porous stones at top and bottom and taken from the mid stratum at the mid depth of the clay, and 70% of consolidation was attained in 6.67 minutes. And what we need to find out is that time required to obtain 70% consolidation of the clay stratum, and the magnitude of the settlement in that time. So, magnitude of the settlement in that time. So, an iodometer test was actually performed on a clay sample of 30 mm thick and drained on both sides and taken from mid stratum depth shown, and 70% of consolidation was attained in 6.67 minutes. So, find the time required to attain 70% consolidation of the clay stratum and magnitude of the settlement in that time. So, this is a particular cross section, a levee cross section where the sand embankment or a levee embankment is actually placed, and this is the clay, and we have got 2 meter and 7 meter is the thickness of the clay, and this is the element A, which is E naught is equal to 1, Cc is equal to 0.2, and gamma sat is equal to 20 kilo per meter cube, and here is gamma 18 kilo per meter cube. Water table location is somewhere here. Now, the solution works out like this. Since the soil is the same clay in the laboratory and in the field, and both are actually 70% consolidation. So, first what we can do is that we can by the quotient of consolidation will be same, because what has been done told is that soil is same in clay in the field. Since the soil is the same clay in the laboratory and in the field, and both are actually having 70% consolidation. So, time factor TV is equal to TCV by H square. So, we can write it as CV is equal to T suffix V HDR square by small t, and which is can be related as because CV in laboratory is equal to CV in prototype, CV in field, they are same. So, TV HDR square by T laboratory is equal to T capital V suffix V HDR square by T field, they are same. So, with that what we get is that T field by T laboratory is equal to H field square by H laboratory. So, T field can be obtained like this, T lab into HF square by HL square. So, we actually have measured T lab as 6.67 minutes into HF is actually given as 7 meter thick clay. So, we actually have said that this clay is actually having a thickness of 7 meters. So, 7 divided by the thickness of the sample is 30 mm, but is actually is doubly drainage. So, what we are doing is that 30 by 2, that is nothing but 1.5 centimeter. So, to equalize the units we have taken in centimeter units, and with this what we will actually get is that the time which actually takes place in the for 70% consolidation is about 2.76 years. That is one thing which we have to note down. The time in the field is about 2.76 years. So, if this type of situations are there in the field, there is a possibility that the settlement actually can affect the structure. And if the settlements are actually occurring say beyond say 30 years or 40 years or so, and if the design life of the structure is actually small, then we need not really worry about that. But if this is the situation, there is actually need for understanding and eliminating these settlements. Otherwise, the structure is actually going to be subjected to distress because of the consolidation settlements. So, the amount of the settlement of the takes place for 70% consolidation can be estimated like this, which is, we know that degree of consolidation is nothing but 70% consolidation at let us say settlement at 70% consolidation to final consolidation settlement. So, we know the final consolidation settlement expression. So, we used this. So, delta H 70% is equal to 0.7 Cc by H, H full thickness 7 meters we have to take now, 1 plus E naught log P naught, that is sigma naught dash plus delta sigma dash by sigma naught dash. So, the in situ stress at mid clay stratum before the surcharge applied we can calculate, that is the effective stress we can actually calculate, and delta P dash or delta sigma dash is nothing but 72 kilopascals, and this can be calculated as this unit weight of this which can be calculated, that is the unit weight of the sand surcharge, and with that is the increase in the load. So, with that what we will get is that the 70% of the amount of settlement that takes place at 70% consolidation can be obtained as 70% of delta H, which is nothing but 0.7 times Cc Cc is nothing but 0.2, which is actually given, into h, which is 7 meters, divided by 1 plus E naught, and E naught is equal to 1. So, it becomes 1 plus 1, and log to the base 10 sigma naught dash, that is the stress at this particular point, is effective overburden pressure, and that is nothing but 71.7, which is actually computed here, plus 72 is due to this levy which is actually there. So, because of that, what it actually estimates is that, so at the center the settlement is actually of the order of 148 mm, and which actually is above the tolerable limit of say 50 mm. So, in that case the structure is actually going to suffer distress. For example, this is then this cause the differential settlements for a levee, and which actually can hamper with the integrity of the system. So, the amount of the settlement that takes place at 70% consolidation, here what we need to understand is that the degree of consolidation is determined by settlement at any time to final consolidation settlement. So, settlement at 70% consolidation divided by the final consolidation settlement. So, because of that, what we have done is that degree of consolidation is given as 0.7. For that, what we have taken is that the settlement at 70% consolidation is actually obtained as 0.7 into the expression for the final consolidation settlement we have used here. So, with that, what we have got is that at 70% degree of consolidation, what is the settlement of the particular levee at the mid stratum depth. So, mid stratum depth the settlement has been computed, and this is actually worked out to be around 14.8 centimeters. So, here also we can look into that here, that if you are having if you take if you divide the clay into number of small incremental thickness, let us say 1 meter, 1 meter, 1 meter, then each depth each thickness, if the settlement is delta 1, delta 2, delta 3, like that delta 7, then what we need to do is that we have to calculate what is the increase in load due to the so called the trapezium load which is there. That is, if you do the method of superposition, I can use for this triangular load, this trapezium loading and this trapezium loading, then we can actually get the settlement at this particular point. With that, we may actually get the more accurate estimation of the settlement. Let us take another example, where in oedometer test is actually performed on 100 meter thick specimen, drained and top at bottom, and it was observed that 45% consolidation, the time factor was 0.15, and which was attained at in 78 hours in the laboratory. And we need to determine the time required to attain 70% consolidation is TV is 0.45 in a job site where the clay stratum is shown in the figure. So, we have got sand layer and the sand layer at the top and bottom, and the clay layer which is at the center here, that is 7.5 meters thickness, and let us assume that one dimensional consolidation is actually valid here, and there is a building load which actually imposes certain amount of delta sigma on the soil. So, this is the water table location here. So, what we need to find out is that we need to find out what is the time which actually takes in the field. So, if you see that the coefficient of consolidation is actually same for the lab and field samples, again by using the same discussion whatever we had, which actually says that CV is equal to TV into HDR square by T. With that, we can actually compute time in field, and which actually works out to be the time in field is actually something like 134 years to attain 70% consolidation. So, sometimes actually this appears that for a given type of clay, that the settlements actually continues for about 134 years of time. So, if you are actually constructing a very important structure on that, and if the clay is actually undergoing the consolidation like this, and this is actually is a proof that for the the Leaning Tower of Pisa, even after 400 to 500 years actually is undergoing consolidation. This is a classical example. So, if you are actually having this type of situations where the settlements are actually coming, predominant settlements are coming within the design life of a building, then it is actually better to accelerate the consolidation settlements. So, in such situations, if the significant amount of consolidation settlements can occur in the design life of a structure, there is a need for the accelerating the consolidation of a soil. So, for that there are couple of methods which actually we will discuss in the next lecture. So, with that what will happen is that we will be covering in this particular module the methods for accelerating the consolidation settlements.